Hello everyone, this is a review for SimLab 4, and I'll be assuming that you have built nearly all the tasks except the last couple of tasks. So more specifically, I'll be assuming that you have built up to task 9, okay, and from now we'll be starting with task 410, okay. So what I'll assume is that you have finished all these tasks and you pretty much know nearly everything. Perhaps you might not, what you might not know is what is the function exactly of these two memory units. This is what I'll be discussing right now. Also, I'll be discussing what is exactly the function of this memory address register, and we will be building the controller circuit, which is supposed to be controlling the brainless microprocessor. Okay, so let's start first with these memory units. These are actually memory units so that you can write down whatever data that you have. You can write it on any of these memory units. So you can write it on this memory unit, which is this register, or you can write it on this register. We'll call this 1 by 4 bit output port, and this is 1 by 4 bit RAM. Okay. So you might choose to store either here or to store in this register. Okay. So how do we really store the data? So let's assume our naive example, which was adding 3 plus 5, and the result is 8. The result is stored here at the accumulator register, and what we want is to store whatever in the accumulator register. We want to store it, let's say we want to store it in this memory unit. Okay, the same goes for this memory unit, but I'll be working on this memory unit. Okay, so let's assume that we have 3, okay, stored in that RAM, and we have 5 here, and we want to add them together, and we want to store them in this memory unit. Okay, so we have a 3 and a 5. So let's first of all reset the circuit. First of all, you know that this reset is this is called a tunnel. Okay, so this is a switch and connected to this tunnel, which is a wire, and this wire is connected, means that it is implicitly connected to all the resets in the circuit. So this reset, this reset, this reset. So how do you build the tunnel? You go to the wiring and you go to tunnel. Okay, and let's assume that we want to build to the clock. Okay, so right now it is connected to the clock, and we call it clock. Okay. Okay, so right now this holds the clock. So instead of connecting this wire to each clock, like this clock and the rest of the clocks in the circuit, I'll build this tunnel and build another one, or copy and paste it, okay, and connect it here. So right now this wire is connected as if I'm connecting this switch to this this wire explicitly, but it is not implicit. It's not explicitly drawn. Okay, the same goes here for this clock. As long as you name them the same name, clock, and make sure to double check the spelling. Okay, then it will be connected to all the clocks in the circuit. Okay, so let's reset the circuit. Okay, okay, and we tick the clock. So right now we have a 3 over here, and which is stored at the accumulator register, and we have 5 coming from this memory unit. So right now we want to put the A only to be 1. Okay, so that in this arithmetic logic unit becomes an addition. Okay, previously it was a pass-through, right now it's an addition, and we tick the clock again. Okay. So right now the 8 has been stored at the accumulator register. Okay, right now the 8 what we want to do is to load this 8 to this memory register. So how do we do that? Of course we need to enable this memory register by controlling these M gates through this decoder. Okay, so first of all we need the decoder to hold the value of that activates this register, which is the value of 15, because the 15 is connected to what enables this register. Okay, which is value F. So I'll put here F because this is the only controlled thing that I have. Okay, so here is F, and I'll try to move this F, pass it to this decoder so that it activates this line. Okay, and activates this memory register. Okay, so remember that I need to pass the F to the input of this decoder. I cannot pass it except through this memory address register. Okay, why is that? Because the program counter does not really, I cannot control the F to be passed to this program counter, and this is why we have created this memory address register so that it can pass this value to the decoder. Okay, so although this memory unit holds an address, it does not hold the data like the 3 and the 5 that we had before, but who cares, as long as we have this as long as we treat this as an address, not as a data, then we could move it to this decoder. So how will it get moved? Remember that this is an F and it is holded on the data bus, and the memory address register has an input of a data bus. Okay, so right now I want to move, so right now it has been moved at the input of the data bus, at the input of this memory address register. So how do I move it to the output? I need to enable the memory address register. I need to enable this register by enabling the load MAR. Okay, so I'll load MAR equals 1. Okay, and at the same time I need to do the I need to tick the clock in order to move the F from the input to the output. Okay, but before I tick the clock, I need to make sure that this 8 won't be lost. If I tick the clock directly, the 7, which comes here, will be passed to the accumulator register. So this is why I need the load ACC. I need to set it to 0. Otherwise, this 8 will be lost. Okay, so that's why I set it to 0. And then when we tick the clock, the F is passed to the input of the multiplexer. Okay, right now I can toggle this input, which is use PC, use program counter. I do not want to use program counter anymore, and this is why the F has passed to the decoder, and pin number 15 is being activated. Okay, what is missing right now is to set read equals 0 and write equals 1. I do not want to read anymore from any of these memory units, and I want to write to one of these memory units. Okay, so right now this has been enabled, and it can it can pass the data from the input to the output. But what data it needs to pass? I need to have this data, which is the 8, which needs to be at that input, which is the input to this register. So I need to activate this buffer. Okay, this 3-state buffer. ACC to data bus needs to be activated, so I'll set it to 1. So right now I have this 1. Okay, so I need right now to tick the clock. Once I tick the clock, I'm pretty sure that the input will move to the output. Okay, but before that please make sure to deactivate the load MER and set it to 0. Otherwise this 8 will be passed to this F again, okay, which is something that I do not want anymore. I want this F to be kept. Although it doesn't really matter, even if it was messed up, even if you have lost this M, you have already it might because of the delay, this 8 might be passed, but right now till now I need to load MER and set it to 0, okay, so that this F is not lost anymore, okay. And then right now, once we tick the clock, the 8 is right now stored at this register, okay. And if you move the ACC to data bus to 0, right now this data bus does not hold any data anymore, okay. If you want to do any operation on this 8 at any particular time, this 8 is, as long as you do not press the reset, which is here, this 8 will be kept and stored whatever you want to do, okay. So if you want to operate on this 8 again, this memory unit can be treated as a storage unit. It is in fact a storage unit and can be and move this 8 to this arithmetic logic unit. How do I do this? By treating this memory unit as a memory unit that I want to read from. So I set read equals 1 and write equals 0. Okay, so right now this has activated this buffer, okay, because this AND gate is activated through the 15 and through the read. Okay, so right now this buffer is activated. So now the 8 passes from this memory unit, the output of the memory unit, to the data bus. And the data bus, if you track it, you find that it will carry the 8 to the input of the arithmetic logic unit, so that you can do whatever you want, either invert it or do arithmetic or logic or whatever you want to do. Okay. So this is the the benefit of these two memory units. The difference is that this memory unit does not have any output port. We cannot read anymore from this memory unit. This is why it's called only an output port. But this is a random access memory, a RAM, where you can store the data and read it from the input from this memory. Okay. What I want you to do is find out how you can store the 8 at this address unit, at this output port. Okay. Okay, let's move on to the control unit, which is the design of this controller that controls these control units. Okay, as you have seen, these control units, these control inputs are control inputs, but we operate on them by ourselves. We need to change them by ourselves. So why don't we build up a circuit that controls these control inputs, so that all you need to do is to just tick the clock, and the 3 is fetched, what we call fetched, which means read from the memory, and then the 5 is read from the memory, and then the addition operation is operated on both. Then if you might want to add some more commands or instructions to let this 8 that has been added to be stored again in this memory unit, then you can do this. But all of that needs to be automated. So this is why we are going to build this controller, which does this task. Okay, let's first find what the controller is. As we have seen previously, the controller needs to be controlled by a counter. Okay, so if you look at this scheme, the counter, we have built a counter here that counts for the decoder. Okay, and we can feed this counter. This counter can feed the controller that we are going to build. Okay, the counter can feed this controller, but we will not do that, we will build a counter specific for this controller, and we will not use the counter that we have used before. And you'll know later on why we have done this. Okay, so let's build a counter specific for this instruction decoder PROM. So this is the instruction decoder. This is what we have built, and we want to build its own counter. So what are we going to do? We have built the controller. This is basically the controller that we have. What we care about are these parts. Okay, these are the inputs that we have seen. Remember that we need, these are 9 inputs. Okay, 1 2 3 up till 9. Okay, and this is exactly what the controller will be controlling. Okay, 9 inputs. Of course, these are a total of 16, but 9 of them that you already know, and the remaining we will discuss them later on. Okay, so the controller, we expect that the controller controls these inputs, which are 9 in addition to 7 more. Okay, so what are we going to do? We're going to build a ROM. Okay, the ROM is something that we have studied before. ROM is built from under the memory. Okay, and you can pretty much use the ROM. You decide how many bits it needs, how many address bits it needs, and how many data bits. We have used 2 and 16. Okay, 16 for the outputs. Okay, which builds this ROM. Okay, so right now we have this is a 2 by 16, 2 inputs and 16 outputs. 16 maps to all these outputs. Okay, and we have built a register which is a 2-bit register. Okay, the number of data bits for this register is only 2. Okay, and then what we have done is the following. Let's look at this ROM. We have stored here 1, 2, 3, and 0, which is, these are all in hexadecimals. These are 4 hexadecimal characters. These are 4 hexadecimal characters, 4 hexadecimal characters, and 4 hexadecimal characters. Okay, this is 0001, 0002, 0003, 0000. Okay, let's assume we want to tick the clock and see what happens, and then let's find out why that happened. Okay, we first reset. Okay, and then we tick the clock. 1, 2, 3, and resets back to 0 as we expected. This is the behavior of a counter. Okay, so right now we have built a counter, but how did we do that? First of all, we know that these are 2 bits, okay, which are controlled by the output of this register. Okay, so the output of the register tells us which exactly location are we operating on, what is the state actually is of this counter. Okay, so we have seen that this state register counts 0, 1, 2, and 3 and resets back to 0. Okay, so let's have a look at what the state is. We know that the state is this is the present state. If you are in the present state 0, okay, then we want the next state to be 0, 1, which is state 1. And if we are in state 1, we want to be in state 1, 0, which is state 2. Okay, this is next state bit 1, next state bit 2, bit 0. Okay, so this is state 1, and this state, we are in state 1, so the next state becomes state 2, and when we are in state 2, the next state becomes state 3, 1, 1, and when we are in state 3, the next state resets back to state 0. Okay, so the input of this state register are these 2 next states. next state bits. Okay, this is why we connected the output from here to the input of the state registers, and this is a 2-bit output. Okay, these are 2 bits, so we have taken this 16 bits and we have used only 2 bits. Let's have a look here at the schematic. So this is a switch, okay, this is a splitter, okay, with bit width 16 and 1 fan output. We have used only bit 0 and bit 1, okay, while the remaining we have not used them. Okay, let's have a look at, let's zoom in. Okay, so only bit 0 and 1 are only used, while the remaining are not used. Okay, the remaining bit 2 till bit 15 are not used. Okay, which is the same as if you have actually connected these 2 bits to the input of the state register, but we have done it through this splitter, which is basically the same. It doesn't really matter that much. Okay, so this is what we have done, and let's get back to our schematic here. This is the table of the state diagram table. Forget about the rest. These are the 15 bits or the 16 bits, which are these outputs. We care right now about these two, which is next state bit 0 and next state bit 1, 0 and 1. Okay, so right now when we are in state 0, we assign this 0, 1. When we are in state 1, the output of this instruction decoder will be 1, 0. And when we are in state 2, which means that this register has an output of 2, which is 1, 0 in binary, then the output of this ROM will be 1, 1, okay, and so on. So how did we tell the ROM to give us an output of 1, 1, for instance? We mapped this, all these numbers, to its equivalent hexadecimal, with this being the most significant bit and this being the least significant bit, which is 0003. The same goes for this column, the same goes for this column, and the same goes for this column. Okay, so this is why we have done 0001. So when we are in state 0, then the output will be 0001, which means that bit number 0 will be 1, while the remaining will be 0. Okay, this is of course in hexadecimal. The same goes here for bit 1, and so on and so forth. Okay, and these are the equivalent numbers that we have stored. So remember that these 2 bits are the ones that control the state, while the remaining they control something else. We do not really care about them. This is why we have put them zeros, but you can put them any values that you want, as long as they are zeros or ones. You can put any values, and these are the values that matter, that lets you hop from a state to the other. Okay, and this is why whenever we toggled the clock, it counts from 0 to 1, 1 to 2, 2 to 3, and 3 to 0 again. Okay, right now we have seen that we can only act on over 4 states only. Okay, we cannot act over more than that. So if you need more than that, then you need to increase the state register, or you need to do something else, and this is what we are going to do. But keep in mind is that what we have right now is only 4 states. So you can toggle between 0 to 1, and 1 to 2, 2 to 3, and 3 to 0 again. Only 4 states, which means that you can hold only 4 instructions. Okay, this will be sufficient for us, but if we need to learn how to design a microprocessor or a controller that can accommodate more than 4 instructions. Okay, so what are we going to do? The only thing that we need to do is to increase the address bit, because this address bit is only 2 bits, and 2 power 2 is 4, and this is why we had 4 states. So right now what we are going to do is we are going to increase it to 6. Okay, of course this means that the state register needs to be increased in dimension. Instead of 2, it needs to be increased to 6. Okay, but we're going to do something else instead of this. Instead of increasing the state register from 2 to 6. What are we going to do? We're going to let this splitter to be bit width 6, and only 2 of them are used. Okay, so pretty much we haven't changed anything right now. It's the same. Only bit 0 and 1 are used in this splitter. Okay, bit 0 and 1, while the remaining are not used. Although they are fed here to the splitter, but they are not used. So how am I going to use them? I'm going to use them with another keypad. Okay, so this is a keypad that has 4 bits, and this is why I'm controlling bit 2, 3, 4, 5, as opposed to here, where I'm controlling only bits 0 and 1 only. Okay, so right now let's reset everything. Okay, we are right now in state 0. Okay, and we can toggle the clock 1, 2, 3, and 0, and it will reset back to 0. Why did it reset back to 0? Because we have put these as zeros. Okay, first of all let's have a look at these at the inputs of this raw instruction decoder PROM. As we have seen, it has been extended from 4 memory inputs to 4 by 16, which is 64 memory inputs. Okay, so what we are going to do is that we're going to assign this 1 again, 2, 3, and 0. Okay, so I'll just upload it right now. Okay, which means that 0, 0, 0, 1, 2, 3, and 0. 1, 2, 3, and 0, 1, 2, 3, and 0, and so on and so forth till the end. Okay, so why did I do this? Because this is what exactly I'll be doing. So let's assume that we want to reset it and clock it again. It goes to state 1, which means that the next state will be 2. Okay, the next state is 2. The next state should be 3, and the next state is really 3. And then right now the next state should be 4. Okay, so when I say that the next state should be 4, I need to control it from this input, which means that it will move me from this memory location. These 4 memory locations will be from this memory location to this memory location. Okay, again, let's put it on 0. We are right now at the 4th memory location, which is 0, 0, 0, 0. Okay, that corresponds to here. That corresponds to this 0. Okay, and this is telling us to reset back. But instead of resetting to this value, we want to reset to that value. Okay, so in order to reset to that value, you need to toggle this keypad. Okay, which is the least significant bit of this pad, which is basically bit number 2. Okay, so here is 0, 1, and bit number 2, which corresponds to 4. Okay, and then let's toggle. So we went to this state. So why did we pass by this state? Because it's a melee machine. So this is why we will get to that, but this is basically why you need to tick the clock first and then see which state it went through. Okay, let's tick the clock again, it goes to that state. Tick the clock again, goes to that state, and goes to that state again. Okay, if we want to tick the clock again, we need to set this to 0010. Okay, and tick the clock. It goes to memory location number 8, okay, which is this memory location 08, which is this one. How do I know that? Because there is a 08 over here, okay, and it will keep continuing as long as you tick the clock, okay. And to overcome this this problem of being a mealy machine, we are going to connect this keypad to a register instead of directly connecting it to this instruction decoder PROM. Okay. Okay, this is basically what I'm going to do. Okay, so let's tick the clock. What is this register? This register, actually, it's an instruction register. It takes the value here and just synchronizes this keypad to the clock. Okay, so I've built already the clock, and remember that this is 4 bits. Okay, this is why I was able to connect these 4 bits to this register. Where do I get this from? The same place that I get this from, which is here, register. Okay, so let's try this. Let's reset it from the beginning. Okay, this is supposed to be 0. Okay, let's reset it. 0, 1, okay, and then 2, 3. Okay, but here I forgot to put this as a 1, so I'll do it from the beginning again. 0, 1, 2, and then I'll put here 1, and then toggle it, go to 0, 4, 0, 5, 0, 6, 0, 7, 0, oops, forgot to toggle it. Okay, so again 0, 4, 0, 5, 0, 6, 0, 7, and then 1, 0, which means 0, 8, 0, 9, 0, A, 0, B, and so on and so forth. Okay? So remember that this corresponds to what? Here what we have is this value corresponds to the 4 most significant bits that are fed to this address, while these 2 significant bits correspond to the 2 significant bits of this address. Okay, remember that this enable is always enabled. Okay, we did not connect it to anything, so it's by default assumed to be enabled. But what we are going to do is that we are going to connect it to this control bus. Okay, and we are going to call it. Remember that this is an enable, which is a single bit, only a single bit that controls this register. This bit we have mentioned that it is only it corresponds to bit number 2 out of the 16. So this is an input of 16, okay, and has only one output, which is bit number 2, while the remaining are not used. Okay, so let's look at bit number 2 here. What does it correspond to? It corresponds to load IR. Okay, so load IR needs to be always 1 in order for us to use this activity. If you do not connect this like that, if you do not connect it, then by default it is 1. Okay, but we are going to connect it. Okay, and this is why we need to set this to be 1 always. Let's look at this scheme. We have set the load IR, which is pin number 2, we have set it always to 0. But right now we want to set it to 1s. Okay, so instead of having this 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, we'll keep it the same, but for load IR we'll toggle all these 4 to 1s. Okay, as here, while the remaining will be the same. And this is why if you read this in hexadecimal, it will not be 0, 1 anymore, or 0, 2, 0, 3, and 0, 4, and 0, 0, 0, but it will be 0, 5, 0, 0, 0, 5, 0, 0, 0, 6, 0, 0, 0, 7, and 0, 0, 0, 4. Okay? and this is what we need to do here. Okay, let's have a look at this. Okay, so we need to change this 0, 0, 0, 5, 0, 0, 0, 6, 0, 0, 0, 7, 0, 0, 0, 4. Okay, which corresponds to the load IR will be 1. Okay. Okay, so right now all of them are loaded. And as you can see, always load IR will always be 1. Okay, let's try that. As you can see, it always shifts among these. And this is the state that we always read. Okay, and you can tell it pretty much the same. Okay, so right now we want to make use of this controller in order to control our microprocessor. So how are we going to do this? Let's look at what we have. We have here 1, 2, 3. Those are load IR is this bit. Next state and are 2 bits. These are the bits that control this circuit, this controller circuit. So these are 3 bits plus 9. That's a total of 12 from 0 to 11. Okay. So this is bit number 11. Okay. While the remaining 4 are unused. So why didn't we put them down to only 12 bits instead of building a 16-bit ROM, instruction decoder ROM? The reason is because in the market, if you want to implement this in hardware, you'll always find that either it is an output of 8 or 16 or 32 and so on. So this is why you'll not be able to find an output of only 12 bits. Okay, so this is why it's more convenient for us to implement it using a practical PROM. Although nothing will actually change if you remove these numbers. And anyway, we always assume that they are don't cares, and the don't cares are converted to zeros. Okay, which are the four most significant bits. Okay. So let's assume right now we want to add the 3 to 5 and then have the value of 8. So as we expect, we have only 3 cycles. 1 cycle, cycle number 2, and cycle number 3, which corresponds to the stop. So the first cycle corresponds to the load ACC. We load the value 3 and then add the value 5 and then the stop signal. The next bit, of course, as expected, 0, 1 when we are in state 0, and then when we are in state 1 we go to state 2, and when we are in state 2 we keep at state 2, we remain at state 2 because it is a stop state basically, we want to stop. This is why it is kind of a halt, and you will not be able to go out of this state unless you reset the machine again, which is basically the implementation of a stop signal. Okay, so what about the implementation of a load? All you need to do is put a read equals 1, load ACC equals 1, and use the PC equals 1, and the remaining, as you already know that. So this, if you read this, it becomes 0551, 0752, and 0002. This will work if you implement this, if you put these numbers inside the this controller, then it will pretty much work the same as you expect. But remember that this load ACC is the first clock cycle, add to ACC is the second clock cycle, and the stop signal is the third clock cycle. And this is why you expect, when you load the ACC, when you want to load ACC, you want to load it with number 3. So you expect that number 3 will be stored in this value. Okay, this is why I've stored number 3 in the first clock cycle. Okay, again, what about number 5? Number 5 will be stored in the second clock cycle. Okay, this is why I've stored 0101 in 5 here, while the remaining we do not really care about them. Okay, so everything will be 0. Okay. Okay, let's look. Let's first of all move these. So if we want to copy and paste these to the to this to add this to this circuit, I've actually added it already. All what we need to do is to copy and paste this, move it upwards, and then connect it like that. Okay, and then we do not need these anymore. Okay, because we have already built the tunnels in these. So these basically are just connected like that, but to decrease the space, I've put them all together at the same line. But these are just the tunnels that, for example, read is connected to this read, and USB-C is connected to that one, and so on and so forth. Okay. So what you need to do is connect this and write down here the numbers that you have already. Some people put it on this format as in the book, as in the manual. I prefer to put it on that format, which is more readable. So this is the first, second, third, fourth, and so on and so forth. Okay. All you need to do is to load these numbers. Load the numbers that we have here: 0551, 0752, 0002. Load them here in those 3 clock cycles, and the remaining are zeros since you won't need them anymore. Okay. Okay. Right now, what we are going to do is to make a little bit of modification. Okay. As you have seen, load ACC is implemented on a single clock cycle. The same goes for add to ACC, and the same goes for the stop signal. All of these instructions are done over a single clock cycle. Okay. In reality, this is not the case. In reality, what happens is that the load ACC is done over 4 clock cycles. The add to ACC is done over 4 as well. The stop is done over 4 as well. Why do we need that? Because some commands, actually here we were lucky. Load ACC by itself, by nature, it does not need except a single clock cycle only. We call it actually a micro instruction. This is called load ACC is called an instruction, and it needs only a single micro instruction. This is why it needed a single cycle. But some other complicated commands, some other complicated instructions need more than one micro instruction, which means that we will need more than one clock cycle. Some commands might need 2, some commands might need 3, some might need more, and so on. And this is why we'll make our microprocessor generic. Perhaps you won't see instructions that can be processed in more than one micro instruction, or more than one cycle this semester, but later on in some like microprocessor advanced class, you will see kind of these instructions. So how do we do that? So load ACC will be implemented on a single micro instruction out of the 4, while the remaining we will be actually silent. This is why you expect a lot of zeros here in these and the remaining. Okay, so let's first have a look at the load ACC. I have chosen to use the second micro instruction, which is the second cycle, to act as the load ACC, while the remaining I'll put them as zeros. Why did I do this? I'll let you know later on. But for now, let's assume that we want the load ACC to be implemented in the second micro instruction, which is the second cycle. The same goes for the add to ACC, and the same goes for the stop signal. Okay, so as we have seen here, the next state bit 0, next state bit 1 have not changed. 1 0, 0 1, 1 1, and 0 0. Okay. These are the two least significant bits. The same goes here, the same goes here, and so on and so forth. So we expect to do, once we reset the machine, we expect to have, to be in state 0, okay, and then we go to state 1. In state 0 we will not be doing anything, okay. In state 1 I've programmed it to do the loading command, the loading instruction, okay, and then we'll go, after finishing this cycle, we'll go to state 2. In state 2 we'll be doing nothing, and state 3 will be doing nothing as well, okay. Then after state 3, after going to state 3, we will hop to state 0, which means that it is this state, not back to this state, okay, and you'll know later on how we will be going. So this basically, when we are state 3, we should go to state 0, 0, which means state 0, which is this state, not that state, okay, and I'll let you know how exactly we're going to go to this state. But assume that we went to that state, we will be doing nothing, okay, and then in the add to ACC we will be adding the 5, okay, and then doing nothing, and then doing nothing again, and then the stop signal, okay. So another thing is the first cycle. So, okay, so right now you know how exactly this will go. Nothing, load, nothing, nothing, and then nothing, add, nothing, 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 and then stop, nothing, and nothing, okay. And actually basically it will stop here, it will not even go to these states. This is why it is, when we are state 1, it is 0, 1, so actually we will not be visiting these states at all, okay. Okay, so what about the first, why did I shift this in the second row, in the second column here? Why didn't I do it in the first column? Note that the first column is nearly the same, is really doesn't have any differences than the remaining 3, except for this load IR. Perhaps it might have some small differences, but the only thing that I want you to note is this load IR, which is a 1 here, while 0 is over here. 1 here, while 0 is over here. 1 here, while 0 is over here. Okay? And the second thing I want you to note is this 0115 is what is mapped here, which corresponds to the hexadecimal number in the first clock cycle of the load ACC. 0115 is also the load, okay, in the add to ACC, sorry, and the same here as well, 0115, okay. While the remaining, the add to ACC is different than in 0752, and while here it's 0552, and here it is 0001, okay. So remember that this is the same as that, and is the same as that. Okay, so there is basically something going on here, and this is actually what will let us go. So basically this instruction is what will let us go from 0, 0 to state 0 here, not to that state. Okay, and I'll let you know when we implement it. I'll let you know exactly how this is going to work. But let's put this aside and let's talk about the efficiency of this command instructions. If you look here, you'll find that we have 4 states. We are basically using one of them, while the remaining 3 are kind of wasting. Okay, so why don't we make it more efficient? Instead of ticking the clock here and then ticking the clock here and then waiting for doing nothing in these 2 instructions, why don't we go directly to this instruction directly? So how are we able to implement this? If you look at 0, 1, if you look at state 1, we go to state 1, 0, which is state 2. When you're in state 2, you go to state 3. When you're in state 3, you go to state 0, 0, which is this state. So why don't we copy and paste these zeros and put them here, such that when you are in state 1, instead of going to state 2, you go directly to state 0, 0, which is this state. Okay, remember that it will be that state, not that state. Okay, and I'll let you know how. You'll know later on how, but assume for instance that you know how this will work. So what we need to do is to write down here, instead of 0, 1, we'll write down 0, 0. And thus, when we are in state 1, we will be moving from state 1 to state 0, which is this state. So we are going to skip 2 states actually. Okay? And this is basically what exactly is in the manual. Okay? Let's look at this in the manual in page 12. We are in state, when we are in state 1, the next state is 0, 0, which means that we will go to this state, state 0, and the next state will be state 1. So we go to here, when we are in state 1, the next state will be state 0, which means that we will go to that state. In state 0, go to state 1, when we are in state 1, remain in state 1, which means it is the stop signal, while the remaining are in fact zeros. Okay, and this is why this becomes 0, and this becomes 0, 5, 5, 0 instead of 0, 5, 5, 2 as we had before, 0, 5, 5, 2. Okay, so all what you need to do is to implement, put these numbers, which are the hex equivalent, okay, put them in the instruction ROM, and you'll be able to implement the addition operation of 3 plus 5. But remember that this corresponds to the first clock cycle. This corresponds to the second clock cycle. These two are skipped because we will not actually pass them. They are bypassed because this is state 0, the next state here is 0. So this corresponds to the third clock cycle. This corresponds to the fourth clock cycle. Okay, so the second clock cycle is what the load operation is when the load operation will take place. Load to the accumulator will be in the second clock cycle, while in the fourth clock cycle the addition operation. Okay, and this is why I expect to put the number 3, which is the number that will be loaded. I expect to put it in the second memory unit, which is this memory unit. Okay, so I'll put here 3 instead of being here. Okay, and 0y is this. Okay, and in the fourth memory location I'll put here 5. Why did I put it in the fourth memory location? Because I have the addition operation in the fourth clock cycle. So the second clock cycle corresponds to the load, and this is where, what do I want to load? I want to load number 3. This is why I put it in the second memory location, while the fourth memory location I've put number 5. Okay, so let's get this done. Okay, so as we have seen, I've copied and pasted this in that. Remember that this is a keyboard. Okay, I've copied and pasted it over here. Okay, and replace the keyboard by the data bus. So what is exactly the data bus? The data bus is the tunnels here. So basically, consider that you are connecting the this wire or this bus with which is 4 bits. You are connecting it to that wire. Okay. Okay, let's see exactly what we are going to do. I'm going to put here 1. So here this is 0, this is 1, and I'm going to put here 2. Okay, and let's reset it and try to add the 3 and the 5. So remember here this is a 3 and this is a 5. Okay, while these two intentionally I've put here a 0 and 1 and then 2. Okay, before ticking the clock, we need to make sure that these numbers are stored in the instruction decoder. Okay, so let's have a look at the instruction decoder, the ROM. 0115, okay, 0115, 0550, and 0000, which is 0, 0115, 0550, 4 zeros and 4 zeros. Again, 0115, 0750, okay, so these two, and then 0000, then 0115, 0011, 0001, and the remaining are zeros. Okay? So this is basically the storage, what we have stored here. Okay? And let's start to click the clock. So right now, 3 has been fetched from the memory. Okay? This is, of course, let's reset it from the beginning. Okay, so right now it is 0. Okay, this has a 0. Okay, once you tick the clock, actually it will not do anything, because basically this is what is expected. Okay, we are expecting doing nothing in the first clock cycle. Okay, let's have a look at the second clock cycle. We expect to load the ACC in the second clock cycle. Okay, so we have right now ticked the first clock cycle, and we will tick right now the second clock cycle. What do I expect to see at the second clock cycle? I expect to see this is a 3, and it is passed through to the accumulator and to the input of the accumulator register, and once I tick it, the 3 becomes here. Okay, so right now we are in state, we are in the second clock cycle. The second clock cycle has been ticked. Okay, and since we have ticked the second clock cycle, so we have went to state 00. Okay, which is supposed to be this state. Okay, why is it supposed to be that state? Because due to the presence of this 0115 command. What does this command do? It takes the value of load IR to be 1, okay, which means that this will be activated, okay, and once this is activated, you will be loading the value 1, which is stored from here, which is stored in this memory address location, and it will come over here. So once you tick the clock, this one will pass to the input of this instruction decoder, okay, which basically is the same as if you have written down here 1. Okay, it's the same as if you have written down here 1, and you have enabled this register using load IR. Okay, so we have actually enabled the register load IR by 1, okay, and stored here a 1. Why did I store here a 1? Because I know a priori that the 5 and the load command, the 5 is in the third micro instruction, and the load command and the addition command is in this micro, is in this row, and this row corresponds to 0001, which is this 1 exactly. Okay, so this row corresponds to 0001, and the least 2 significant bits are 00. So in other words, this row corresponds to 000100, 000101, 0001 0001 10, 0001 11. Okay, remember 6 bits correspond to this row. Okay, if you trace it, you'll find yourself that 1 is what needed to be stored in this memory location, and then 2 needs to be stored in this memory location, and then if you have even multiple memory locations, you will be storing here 3, and so on and so forth. Okay, so basically you put a memory location here 0, and then 1, and then 3. So 1 memory location for the address, and 1 for the data, which is 3. 1 for the address, and 1 for the data, which is 5. 1 for the address, and 1 for the data, but here we do not have any data since we have halted. Again, here it is an address. Okay, so load IR, we are loading the instruction register. We want to load the instruction register with some address, okay, in this clock cycle. And in the second clock cycle we want to do something with the data that is stored, which is loading the ACC. Again, here we want to load IR instruction register by 1. What is the instruction register? The instruction register is this register. Okay, is this register, we want to load it, okay, so that it controls exactly which command you want to execute. Do you want to execute this command or that, or let's say it again, you want to execute this command or this command or this command, okay, and so on and so forth. Once you do that, you are basically, you take the clock again. So right now we are in a state we are in state 0004. Okay, let me zoom it in. Okay, which corresponds to the 0750. Okay, which corresponds to the add to the ACC. Okay, take the clock again. So the 8 has been stored here in the accumulator register, while the 2 has been stored. While the 2 corresponds to the halt state, where whenever you click, nothing really is going to take place unless you reset it. Okay, so let's zoom in and let's reset it first. Okay, and let's zoom in to have a look at what happens exactly here. Okay, so here we have resetted the state, so we are right now in state 00. Okay, this is right now we are going to load the accumulator. Okay, and then we want to add right now, so we're going to that state 0750. Okay, and then we are going to halt in that state. Okay, okay, so right now if you look at these, the reason why we have done it this way, because we wanted to skip these two values which correspond to the values in the second and the third clock cycle. So the 0th clock cycles, first clock cycle, second and third clock cycles, we want to skip them, and this is the way that we have skipped this. Okay, so the main motive behind this is to let our microprocessor be expecting some instructions that can be implemented on 4 clock cycles, rather than the load ACC and the add to ACC, which can be implemented only on a single micro instruction, which corresponds to a single clock cycle. What I need you to do is to find out how you can write down a command to add these two numbers, which is the 3 and the 8, and the 3 and the 5, and the number that is stored, which is the 8. I want you to store it in this ROM, in this 1x4-bit RAM. Okay, perhaps you might need the 3rd and the 4th micro instructions, and perhaps you might not need them. So I'll leave this up to you whether you want to try them or not. Whether you want to try to load it through this, or you want to try to load it using a 3rd and 4th instructions. Okay. Okay, so again, what is needed, which is a task. This is actually an extra credit task, which corresponds to this invent your own instruction. Okay, what you can do is do the 3 by 4 addition. Okay, and 3 plus 5 addition, and so it will be basically the same, but instead of stopping, what you need to do is add the store the value 8, store it in the memory unit that we have, that we have designed here, which is this one or that one. Pick up one and store it over there. Okay, I hope that this has clarified a little bit the design of microprocessor. Please try to study as much as possible this microprocessor design, because it really gathers all the information that you have studied throughout the class, and good luck.